the type of problem for the second type?
The second type is
There was 3 types and we didn't finish the second.
Oh, okay. I will go back to that one. I forgot. Let me finish this one because before I came, I just finished one writing, so I go this one first. Basically, for gear system is this. Usually, they for the exercise, we only use 2 gears, and each gear attached to a shaft. In these systems, the shafts are only elastic materials, and gears by themselves is solid. Okay, they have a tube, they have a teeth. Each time as a pair of the teeth in contact, and then move to the other one. Basically, I think if you major in engineering, you would know, but not majoring in engineering. Basically, each time is one gear of the one pair of the teeth, and they have a contact, and then it depends on one is driving, one is driven. And driving apply the force, contact force, to the driven teeth to move that forward. Okay, this is the driving, and apply the force to here to move on, and then they move to the engage in the second pair and just keep going. The actually that is the essential part, how to define, how to design the profile of the gear teeth and to make the things happen. And a good design is this: once the gear is a pair of the gears is engaged, then they would have you shouldn't hear any noise. Okay, if there was any noise, basically indicate the 2 pairs of the pairs of the teeth, they have a sliding. Okay, that is a very bad design. And the sliding or relative motion, that is the resource of this noise or kind of the high frequency sound. And a good design that will have completely transferred all the power through the vertical contact force. Okay. So back to our problems here, and shafts are the only elastic objects. So that means we apply, and only shaft will be distorted, will be twisted, and gears by themselves is only to transmit power and force, and to regulate the rotation of the speed. And to say so, basically gears is working as the compatibility equation for our calculations. And those are the principles. I will be back on this page later on, and I would rather to use the one example directly to show you. This is a very straightforward example, and actually this example in terms of the design is pretty much fit into our previous 2 slides and kind of formulation. So I would like to go on this example very detailed, slowly, and then once we finish this example, we're back to look at the principle here. So for this example here, we have the 2 elastic shafts, which means they would have a twist angle there. And those are the dimensions, and the gears, the size of the gear is indicated by the radius. And the smaller the radius, the less number of the gear teeth. And the larger the radius, which means the larger number of the gear teeth. And to pair the gears, the gear teeth on one must match the gear teeth on the others, which means in terms of the gear size and profile, they must be the same. Okay, so that means for the smaller radius, they would have a less number of the teeth. This one has a large number. So for this case, we are given the rigidity modulus for the both shafts. They are the same. And later I'm going to rewrite this problem statement. And for the shaft, we have the maximum, we have an allowable stress is KSI, 8 KSI. So that is the maximum stress shouldn't exceed this one. So for this question, we want to find what would be the maximum torque that we can apply to this gear system. And the application of the torque is this. We apply the torque, try to twist this shaft. So this shaft is elastic, so it will be twisted a little bit, which means to exhibit the twist angle. And then the torque will be transmitted to this gear, gear B. And gear B is responsible as a rigid body to transmit the power or torque to D, to C. And C, again, will, due to this welding to the shaft here, that the rotation, little bit rotation of the C will drive this shaft to twist it. This end is fixed. So basically, once we apply the torque here, everything will a little bit rotated, but lock in that equilibrium state. Okay, so that is the feeling of this problem. So let me turn off this slide, and then we can do some calculations. So gear set is the last indeterminate problems. An example here is this. We have two sets of the gears, and basically here the shaft is welded or kind of locked into this gear, and here another bigger shaft is here. Okay, and through appropriate kind of support, the bearing support here, I didn't draw it. This is at A, B, C, and D. And at A, we applied a torque. This is the driving torque. And we want to calculate is the maximum torque allowed. And allowed, that means here for the shaft AB and shaft CD, the allowable stress is 8 KSI. Its radius 0.375 inch, and this is 0.5 inch. And the length is 2436. Okay, we have those informations, and basically here, we are given the maximum, the allowable stress. So that means we shouldn't have our applied torque to exceed the maximum stress over the two values. So this is one. So the second one we want to calculate is at the T maximum, so which means this maximum torque, let me call it T maximum. Okay. At the T maximum, we want to calculate corresponding the angle of rotation at A. A is where the torque applied, that is the free end. Okay, so we want to calculate the angle of rotation. And what is the angle of rotation? That is a little bit different from the angle of twisting, and I will show you quickly in this example. And for this case, we can draw the free body diagram, and again we apply the driving torque here. This driving torque will twist this shaft, and again that shaft will once be twisted and get into equilibrium, and then the torque will be transmitted to here, and in turn to here, in turn to this one. And we can use free body diagram to address these kind of things. Let me use this board here. So the free body diagram will be working like this. Let me. This is a gear C. This is a gear B, and we can put it into 4 free body diagrams. And here I separate those shafts. Okay, so this is A, B, and this is gear B. This is gear C, and this is CD. Okay. So we do this kind of we try to follow up the propagations of the torque. And this is where we apply the torque here. And again, for this problem, everything is in static equilibrium. So this shaft, the torque being transmitted to the first free body, and this must be in balance. So that means this torque must be here, right? And the magnitude must be equal to T0. If let me using the double arrow, so for this case the double arrow will be something like this. So if we use the double arrow notation, that would be like this. And on this case, this double arrow should be in this notation, right? Okay, then these gears. And allow me not to draw the gear teeth. That is very tedious. And actually, design of the gear teeth, that is worse. When I was your age, I think that time I take 1 year, the 6 credits because that is so long ago, and the gears is a fundamental tools in mechanical engineering. So 1 year. And starting from that time, we have AutoCAD, but very primitive. So basically, we have all the design things ready. We went to the lectures classroom. They have the designing tables. We just sit there and draw using the ink, and to draw the profiles, and then to benchmark the calculation, all the necessary calculations, and that is for midterm. And I still remember that is. Okay, so now for this one, we've done the free body diagram for this part. And now you can see, because here this phase, assuming we do the welding of the shaft along the parameters at this end, to here, suppose here has some holes on the gears. But anyhow, we assume that this end is welded to the gears, so they have a rigid connection. So that means to this portion, the T now here to this one actually is an action reaction. Are we right? So that means whatever the reaction developed at this end B here will directly go to the gear here. So that is an action reaction. So that is at the same magnitude but opposite direction. Are we okay? And right now here I'm talking is we gradually get into the compatibility equation of the gears. And now we have the things here, how do we translate or how do we describe the torques being transmitted to these gears here. And that will, I will give you more information. And those ones are basically based upon what we call the kinematics of the gear sets. And that is the new to most of you, and that is the new thing you have to adopt for this type of the problems. Okay.
Are you saying that the torque in the shaft is the action reaction, or the torque and the plate? Yes.
This torque in magnitude, this is action, this is reaction.
But it looks like it's also going the other way.
Yes, and on this side, this is an action. On this side, this is a reaction.
No,
they opposite. Yes, they go to opposite direction. If they connected, the pairs will be cancelled.
I'm talking about on the shaft.
Oh, on the shaft here, this is go that direction.
But look at the other way the torque arrow is going.
Okay, let me draw a better way. Like this.
Right, so why is it like that?
Okay, so this way, if we use our finger to circulate,
like this, like this. Right? So here use our forefinger to follow up these circulations. Right?
I think what she's asking is why are we splitting it up? I mean, we know it's twisting this way, and the gear's also twisting this way.
Oh,
We've got the reaction B going that way.
Okay, so let me do this one. So from this end, this is driving, we go this way. No doubt, right?
Yeah.
And then this is to balance, so we have to go in this way, so that go to that direction.
So that's also an action reaction.
So here is the action, here is, we call the balance. Action and reaction is happen at the same place. Action and reaction is a concept happen at the same place.
Well,
And then here we call the balance. It's called the balance. There are two different loads. Okay. So now to here, this side, basically this end, this face is welded to the opposite side of this gear, so basically here. So at the same cross section, this torque will be transmitted to here as an action reaction. So here, this is the action go that way, reaction go in this way. Are we okay? Okay. And now to translate information to here, we do need a little bit more information. And here, let me highlight that one here. So two gears. So one gear is, one is smaller, let me call this is radius RB. And this gear has radius RC. Okay, they have a different size. They are different in size. So the radius for this illustration RB is less than RC. So let me draw that. Okay, now here the RB and RC, that is the gears to mimic the one we exercise here. Okay, and now I want to set up the information we already know. On the gear B, we have the torque that is in this rate. Let me call it T0. Okay. And right now the two gears are engaged and they're ready to transmit the torque. And to even separate, to even get into details, let me take the free body diagram of what's going on here. So take the free body diagrams of each gears. So one gear. Okay, so this is gear RB, radius, and this is RC. And here, let me highlight the point of the contact here. So basically, you could imagine the two gears, essentially, each time they contact, they have only one point of the contact. Okay, and that is where both the profile tangent to each other there. So this is called the contact of the point. Contact. Point of the contact. So here highlight, here is the contact point. And here that's the free body diagram, this is T0. Okay, and now we are ready to explain the transmission of the torque. Again, from the beginning, I mentioned the two sets of gear, this is a driving, this is a driven. So driving is to apply the torque and to rotate through a pair of the engaged teeth. So here you can see, once I drive here, you can see, can you feel on the two teeth, this one apply the force to press this down. Can you see it? So that means at the contact point, here, there, this one, this is the driving, I press down basically on this teeth, sorry. I'm sorry. Didn't record it, right? Okay, this press down, you can feel from the bottom of the teeth, it will feel a repelling force on this side, right? So that means that the contact here